Hello and welcome back to the A-Level Physics channel. My name's Remik and today we're going to be starting section 3.2. Today we're dealing with atomic structure, the strong nuclear force, the standard model and antiparticles and photons. So to begin, something simple. Atomic structure. Atoms are made up of three particles: protons, neutrons and electrons. Protons and neutrons are found in the nucleus of an atom, while electrons orbit the nucleus. Pretty easy stuff. Now we have to talk about the properties of said particles. In this table you can see that protons and neutrons have a very similar mass, neutrons being very slightly heavier, but electrons, being much smaller particles, have a mass of 10 to the power of 4 times smaller than protons and neutrons. When it comes to charge, neutrons are neutral, like the name would suggest. Protons and electrons have equal in magnitude but opposite charge, so it's plus 1.6 times 10 to the power of minus 19 coulombs for a proton, and it's minus 1.6 times 10 to the power of minus 19 coulombs for an electron. As you can tell, these are absolutely tiny numbers. So what we do to make life just a bit easier is assign relative values. 1.6 times 10 to the power of minus 19 becomes a relative charge of 1, and a mass of 1.67 times 10 to the power of minus 27 becomes a relative mass of 1. Now, a stable atom has no overall charge, and since protons and electrons have equal but opposite charge, that means that in a neutral atom there must be equal amounts of protons and electrons. Now, a new concept, let's talk about specific charge. Specific charge of a particle is just the ratio of its charge to its mass, which can be calculated using the formula specific charge equals charge over mass, or using the symbols Q over M. Charge here is in coulombs, mass in kilograms, so the units for specific charge are coulombs per kilogram. Values for the specific charge of the electron and proton are given on the data sheet as the charge to mass ratio. Using that value, we can see how dense an electron's charge is, as it is equal in magnitude to a proton, but has 10 to the power of 4 times less mass. In the exam, you may be asked to find the specific charge of either an ion or a nucleus. So let's go through an example now. The specific charge of a sodium ion. As it's a +1 positive ion, there's one more proton than there are electrons. That means that the resulting charge is 1.6 times 10 to the power of minus 19 coulombs. Mass is the total number of nucleons multiplied by 1.67 times 10 to the power of minus 27, which gives us an answer of 4.008 times 10 to the power of minus 26 kilograms. Therefore, the specific charge of this ion is given by its charge of 1.6 times 10 to the power of minus 19 coulombs divided by its mass, which is 4.008 times 10 to the minus 26 kilograms, and that gives us a specific charge of 3992015.968 coulombs per kilogram. You'll quite often get quite a large number for specific charges of a nucleus. Since I use the phrases nuclear number, atomic number, or mass number in that explanation, let me explain to you what they actually are. Every box on the periodic table has to present certain information about the element in question. The nuclear number, or the A number, the proton number, or the Z number, and the chemical symbol for the element. The nuclear number is also known as the mass number, and it is the total number of nucleons that exist inside of the nucleus. The proton number, also known as the atomic number, is the total number of protons in the nucleus. Now that you know how to read the periodic table, let's talk about isotopes. Isotopes are atoms with the same amount of protons but different amount of neutrons. They have the same proton or atomic number but with different nucleon or A numbers. Let me be clear, they are still the same element. Proton number is what decides an element. The number of neutrons doesn't make it a different element, just a different isotope of the same element. They're all carbon atoms, just with different amount of neutrons in a nucleus. Isotopes, due to their imbalance of neutrons and protons, are unstable. This means that they decay and emit radiation to achieve a more stable form. We'll look over how they decay later, and you'll go into it more in year 13. So now that we looked at isotopes, we need to look at isotopic data. It's basically how many of each isotope there is in a sample. Say we had a sample of carbon. How much of it is carbon 12, how much of it is carbon 13, how much of it is carbon 14. You get the general idea. Isotopic data is useful, and you need to know this. In carbon-14 dating, all living things contain isotopes of carbon. The percentage of carbon, which is radioactive carbon-14, is the same in most living things. So after they die, the amount of carbon-14 inside them decreases over time as it decays to more stable isotopes. Scientists can calculate the approximate age of archaeological finds made from dead organic matter like wood or bone using isotopic data to find the percentage of carbon-14 that's left in the object. Now that we've dealt with the fundamentals, we can move on to the stuff that absolutely blew my mind when I first learned it, the standard model. The standard model explains how the basic smallest building blocks of matter interact and how they're governed by 4 fundamental forces. So the best way to teach you this is to build it from the bottom up. Let's start with matter particles, All matter is made up of fundamental particles, fundamental meaning you can't go any smaller, of which there are two types, quarks and leptons. Each group, quarks and leptons, consists of 6 particles which are related in pairs or generations. The lightest and most stable particles make up the first generation or pair. The heavier, less stable particles make up the second and third pairs, with the second pair being lighter and more stable than the third. The 6 quarks are paired like so. The up and down are in the first generational pairing, being the lightest and most stable. Then we have the charm and strange quark in the second pairing, and finally the top and bottom quark. For our needs in A-level physics, you only need to know about the up, down, and strange quark. But in my opinion, it's very important to get a genuinely meaningful, proper understanding of the standard model to carry on. After the quarks, we have the 6 leptons. The 6 leptons are similarly arranged, and the electron and the electron neutrino are the first generation, the muon and the muon neutrino are the second generation, and the tau and the tau neutrino are the third generation. The electron, muon, and tau all have the same electrical charge, whereas the neutrinos are neutral, as the name suggests, and have very little mass. The same trend in mass and stability goes for leptons too. The muon and tau are essentially heavier, less stable electrons. Now, to carry on building the standard model, we have to move into the realm of true craziness, antiparticles. They do exist, and they're not just Star Trek's scriptwriter's fantasy. All of those particles which I just mentioned have a corresponding antiparticle equivalent. All of the properties will be talked about when we come to it soon, but for now, just know that they're real. Those are all of the particles that make up all of the matter in the universe. Now, moving on from matter particles and onto force and carrier particles. Make sure you understand that these particles, the force and carrier particles, they don't actually make up any matter in the universe. They're just exchanged by matter particles in order to exert a force upon each other, and in some cases they carry charge. There are 4 and only 4 fundamental forces in the universe. The strong nuclear force, also known as the strong interaction, the weak nuclear force, also known as the weak interaction, the electromagnetic force, and the gravitational force. They work over different ranges and have different strengths, with gravity being the weakest, but it has an infinite range. The weak force is the 3rd strongest, but it also only works at the subatomic particle range. The electromagnetic force is the next strongest, and it has an infinite range. Then it's the strong force, which has the shortest range, and as the name suggests, it is the strongest fundamental force. 3 of the fundamental forces are the result of the exchange of force carrier particles which fit into the standard model. These are called bosons. Particles of matter transfer energy by exchanging bosons with each other. That is how force is felt. The different forces are carried by different bosons. The strong force is carried by the gluon. The electromagnetic force is carried by the virtual photon. The W and Z bosons are responsible for the weak force. And although it's not quite been found yet, the graviton should be the force-carrying particle of gravity. Now that right there is the standard model in full. This is every single particle in the whole universe, and it's in a table.
Okay, you're probably thinking, why can you hear Sam's voice and not Remik's voice? But I'm editing this video and I feel like I need to add a tiny bit more detail. You've been told your whole life that protons and neutrons are fundamental particles, and you might be thinking, why are they not in the standard model? That and so much more is explained in the next video. The reason it's in the next video, the amount of words and information that is required to explain it would make this video 30-40 minutes long. So we decided to separate it into the next one. So the standard model is every single fundamental particle in the universe. You can't break these particles down any further. Any other particle that you've ever heard of can be broken down further. And there's a whole host of particles that you will never have heard of that we're going to talk about in the next video. Okay, back to Remik.
Honestly, maybe rewind the video, listen to another person talk about it. Just make sure you really wrap your head around this and fully understand it before you move on, as it will make everything in physics a lot easier. Now that we've covered the standard model, let's talk about stable and unstable nuclei. This is an example of where a good understanding of the standard model helps greatly. There's several forces acting on the nucleons in a nucleus. The electromagnetic force causes like-charged protons to repel. Gravity causes the nucleons to attract to each other, but is very small, as the masses are very small. This means that the force of gravity is absolutely tiny in comparison to the repulsion of the protons. And now, the last force acting is the strong nuclear force. It binds it all together, as without it, the nucleus would simply explode due to the immense repulsion from the protons on other protons. The strong nuclear force is an attractive force that's stronger than the electromagnetic force, but it only has a very, very short range. It is most attractive at 1 × 10 to the power of minus 15 meters apart, or a femtometer apart. It is attractive up to 3 femtometers, but it drops off after that and rapidly falls towards 0. But so that a nucleus isn't crushed to a point, it must be repulsive at a small distance, which we found to be around 0.5 femtometers. With the strong nuclear force covered, let's talk about nuclear decay. There are 3 types of decay, that a nucleus can undergo. Alpha decay, given this symbol, only happens in big atoms, usually more than 82 protons, like uranium. The nucleus is just too big for the strong nuclear force to keep them stable. So to make themselves more stable, they give off an alpha particle, which is 2 protons and 2 neutrons from the nucleus. When an alpha particle is emitted, proton number decreases by 2 and the mass number decreases by 4. For example, uranium 23892 would turn into thorium 23490. Alpha particles have a very short range, only a few centimeters in air. You can test this using a Geiger counter. If you put it close to an alpha source, then move it away slowly, the count rate should drop within a few centimeters. Beta decay is the emission of an electron from the nucleus along with an antineutrino particle. This decay occurs in neutron-rich nuclei. When a nucleus emits an electron, a neutron turns into a proton, an electron, and an anti-electron neutrino. For example, rhenium is turned into osmium by beta emission. Now, the antineutrino particle here just carries away energy and momentum. Originally, we thought only an electron was emitted from beta decay. However, the energy of the particles released was less than that of the particles before the decay. So due to the conservation of energy, we needed something else to be released. In 1930, Wolfgang Pauli suggested the neutrino, and 25 years later it was observed, providing evidence for his hypothesis. Now finally, let's talk about antiparticles and photons. As you may remember from GCSE, the electromagnetic spectrum is a continuous spectrum of all the possible frequencies of electromagnetic radiation. There's 7 types of electromagnetic radiation based on the frequency. I'll list them in order of increasing frequency and decreasing wavelength. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays and gamma rays. The higher the frequency of electromagnetic radiation, the higher its energy. Onto photons. As I'm sure you remember, they're the carrier particle of electromagnetic radiation, and Max Planck suggested that electromagnetic waves can only be released in discrete packets or quanta. Einstein went further by suggesting that these can only exist in discrete packets, which are called photons. The energy, E, that one of these photons carry is equal to Planck's constant multiplied by the frequency of light. Frequency is also equal to the speed of light, c, divided by the wavelength of the wave, lambda. So we can use that and substitute frequency in the equation with c over lambda, and we get E equals hc over lambda. Onto antiparticles. Yeah, they're real, which is crazy, but they only exist for a fraction of a second. Each particle has a corresponding antiparticle with the same mass and rest energy, but opposite charge if they're charged. For an example, an antiproton has the same mass as a proton, but is negatively charged. All particles are known as matter, and all antiparticles are known as antimatter moving forward, and a positron is an anti-electron. If you look at your datasheet for physics, you'll be able to find a table of particles and antiparticles with their relative charges, masses, and energies. Also, in the table, they're grouped as leptons, baryons, and mesons. You'll have heard of leptons, but the other 2 groups will be explained in the next video. Onto pair production. One of Einstein's most famous theories says that energy can be turned into mass and vice versa. When energy is converted into mass, you produce equal amounts of matter and antimatter. This is called pair production. It can only occur if there's enough energy to produce the masses of the particles, and it must always produce a particle and its corresponding antiparticle because certain quantities must be conserved. You'll learn about this in the next video. A common situation for pair production is when a photon passes near a nucleus. Then, an electron and a positron are formed. The photon must have at least 1.021998 mega electron volts of energy to produce this electron-positron pair. We find this by using the table on the datasheet to get the rest energy of an electron and double it. The electron volt, by the way, is just another way of measuring energy, and we use this for very, very small amounts of energy. It's 1.6 times 10 to the power of minus 19 joules, so a mega electron volt is 1.6 times 10 to the power of minus 13 joules. Now the other side of Einstein's theory, mass into energy. This is called annihilation, and it's when a particle and its antiparticle meet. They get turned back into energy, usually photons. Antiparticles usually exist for only a fraction of a second before this happens, which is why we don't get them in normal matter. The minimum energy of a photon produced by the interaction is the rest energy of the particle annihilated as 2 photons are released in annihilation. Now, that's enough for today. If you need a quick reminder on anything, or you don't quite understand anything, just go back to the video, watch it again, make sure you get a proper understanding of this, as the next video will be quite impossible to learn if you don't really get this. You can find everything to do with physics, chemistry and biology on our website, which includes all of these videos nicely formatted, exam question packs and walkthroughs. Thank you very much for watching.